profiling of a house for linear cryptanalysis. The authors are Andrei Bogdanov, Elmar Ischhauser, Philippe Bayer, and Philippe will give a talk.
Thanks. Yeah, so we're a little behind the schedule, so I'll try to make it quick. So this is basically it's more of the same theme as we've seen in the last two talks about trying to improve these estimates of various statistical attacks. So I'm looking at linear cryptanalysis in this work here, which was introduced by Matsui to analyze TDS. And the general idea is that we're looking at linear relations of the input to a block cipher, and we look at the probability of when they are equal to linear relations of the output. And the measure here is this correlation value, and as we can see, well, it depends on which key we use in the block cipher. So this is some key-dependent random variable. And if this value is larger than we would expect for an ideal block cipher, well, then we can use this as a distinguisher. And we can turn just a distinguisher into key recovery. So this is basically what we heard before. We have a distinguisher over, say, R minus 2 rounds here. And we have plain text, ciphertext pairs over R rounds. And we try to guess the outer key bits, decrypt some rounds. If we guess correctly, well, then we'll measure our distinguisher here. If we guess wrongly, then we'll calculate our distinguisher over a much larger number of rounds. So the idea here is that if we have a high absolute correlation, we probably have the right key guess. If we have a low absolute correlation, we probably have the wrong key guess. So the important question here is to estimate how good our attack is. What is the correlation, what is the distribution of this correlation value for both a wrong key guess and a right key guess? So that's what we'll have a look at here. And for a single approximation, when we have this result here, at least for key alternating ciphers, we in theory know how to calculate this key-dependent correlation here. We have a sum over all trails in the linear hall, adjusted by some keys. This is all very fine, but because this is quite difficult to compute in practice, well, the first works did something a little more simple. They assume that for a wrong key, we actually get correlation 0 for any key. And for a right key, we have some, well, the absolute value is some constant, which is just the value, the correlation contribution of the most dominant trail in this hall. So this works for some ciphers, but it's not very accurate in general. So for the wrong key guess here, Damon and Raymond actually showed that for an ideal cipher, which is what we usually model the wrong key guess as, we have this normal distribution here, which is not 0. And for the right key guess for any cipher that doesn't have a dominant trail, so most modern ciphers, this sum will take on quite a lot of different values, and we have some distribution over our key space. So this is not a constant. So this is well, fine for a single approximation, but there have been multiple extensions to linear cryptanalysis that use multiple linear approximations to increase the attack power. The first one was multiple linear cryptanalysis, where we just use some set of M approximations, but the analysis usually requires that we assume that these approximations have statistically independent correlations. And this, well, is kind of difficult to guarantee. To try to kind of remedy this, multidimensional cryptanalysis, linear cryptanalysis was proposed. And this uses all approximations in an n-dimensional subspace. So to some extent this avoids assumptions about statistical dependence, but we might have to include a lot of approximations that the cryptanalyst is not necessarily interested in. So both of these methods here use what we call the capacity to measure the strength of the distinguisher, basically. So this is the sum of squared correlations. This is, of course, also key dependent. And for multidimensional, we can actually calculate it like these multidimensional probabilities. I won't get too much into this. But here we again have the problem that this value here is extremely difficult to say anything about if these correlations are not statistically independent. If they are statistically independent and normal, well, this is a chi-square distribution, but that might not necessarily be the case. So there's been some work on basically figuring out what this distribution looks like for multiple and multidimensional attacks. And the first one was by Huang et al. And they basically gave key-dependent capacity formulas, but only for the right key case. And they express it as a gamma distribution. So they actually explicitly give this distribution. So what they didn't cover in this work was what I call data dependencies. So basically what happens if you don't have access to the full code book and you only you have to undersample basically. What does that distribution look like? They also didn't cover the wrong key case, which, well, then it's kind of difficult to compare right and wrong key guesses. Also, what is lacking in this work is that we assume that we know these exact distributions of the correlations, which are not trivial to calculate. So it would be nice to have some practical way of doing this. Oh yeah, and then we also have usually an assumption of independent round keys. That's not necessarily true either, as we heard in one of the previous talks. And finally, I have a little question mark down here, because this work also makes some assumptions on the shapes of the correlation distributions for this to work, like they have to have mean zero and equal variances. And it's also not clear whether it's very practical to actually pick approximations such that that is the case. So this work was improved by Belgium and Newport, and well, they tick some more boxes here. They get the data dependence included. They get the wrong key case covered. We still have this assumption on the key schedule. We also still don't, well, we have to know the exact correlation distributions or probability distributions. And while they do relax the requirements on which correlation distributions we use, they still have equal variances. So they further improved this to remedy some points here. So now we don't really have any restrictions on what correlations we can use. And they also give a practical way to estimate the correlation distributions. But what you kind of lose is that you don't no longer have an explicit formula for what probability distribution the capacity actually is. So you only get the mean and the variance in this case. Okay, so a word about independence assumptions here. We have this assumption on independent round keys, which is not necessarily the case for both ciphers, and we actually show in our paper that the capacity can actually change shape, the capacity distribution changes shape when you change key schedule. So in particular, you cannot necessarily assume that the joint distribution of your correlations is multivariate, which usually makes your analysis much easier. And also, Newport recently indicated in some results that there seems to be some connection between linear dependence and statistical dependence of correlations. And this seems to be very problematic for the wrong key model, because here we usually use that approximations are independent. The impact of this is basically that we can only express the wrong key model for linearly independent approximations. And this is also what we'll do in this work, because we simply don't know how else to do it. So if you can figure this out, that would be really nice. But anyway, as a step in the right direction, we propose multivariate linear cryptanalysis, which I'll explain to you now. So as I said, we'll still have this little restriction here. In practice, I'm not really sure if it matters too much. But I have like a three-step model here. So the first step is extremely general. The wrong key model, we simply say, is a multivariate normal distribution with zero mean and this covariance matrix here. And the right key model is not so useful. It just says that the right key distribution follows some multivariate distribution. So it might look really weird, like this blue weird thing here. So yeah, this is just a one-dimensional case. I can't really show the m-dimensional case. So this is not very useful. So what the next step does is to kind of make this practical. So for this we use this method called signal noise decomposition, proposed by Bogdanov and Tischauer in 2013. And the idea here is that you know some trails of the linear hull, and then you kind of model the rest of the linear hull as noise. So we have some part that we call the signal, which is a bunch of good trails. And then we can estimate what we call the signal distribution. So basically the sum I showed you before, but restricted to this signal set here. And then we can just calculate this partial sum for many key values and get some idea of what this distribution looks like. And the rest of the whole we just model as this noise distribution here, so we add this distribution to whatever distribution we got up here. So that in the multidimensional case, well, the wrong key is still exactly the same. And the right key, well, we have this now multidimensional distribution that we measure from the signal, so that's just computing the sum I showed you for multiple approximations at the same time. That might be this really weird blue distribution down here. And then we add this noise term, which is now a multidimensional normal distribution. So actually the same distribution as we have for the noise up here. And that just serves to kind of smoothen out this distribution here and hopefully be something that's really close to what the actual correlation distribution looks like. Okay, so this is fairly good. The only problem here is that now I'm only saying what happens if we actually have the full code book available and can measure everything exactly. So we need to deal with this undersampling phenomenon. So if I now only want to use n plain text ciphertext pairs, what happens? And luckily here we have a result from Murphy that we can use in a pretty straightforward way. So the wrong key, we have this distribution we had before, which is this curve down here. And then we just have to add some extra things in the variance. And this is this diagonal covariance matrix with entries of 1 over n. So that just stretches out our distribution. Clearly the fewer text we have, the less good an idea we have of what this distribution actually looks like. And for the wrong key, for the right key, sorry, this is exactly the same. We have the distribution that we had before. We add this undersampling term here, and we get this. So the bottom line here is that now we can actually, for any set of approximations, linearly independent, where we know the signal here, we can actually calculate what these two distributions look like, and from these two distributions we can figure out basically what our attack advantages. So this is how we would compare ourselves. So obviously we have more green tick marks, so that's good. So we fix this arbitrary key schedule here. Like when you calculate your signal, I don't really care what key schedule you use, I just compute the sum. So I don't need any assumptions on the key schedule. And well, explicit capacity distribution, we can't necessarily give you a closed form depending on the cipher, but we can at least allow you to efficiently sample from this distribution as much as you want to. So I put a little star on these here because of this result by Newport. We don't really know how to express the wrong key distribution when we have linearly dependent approximations, but hopefully someone will come along to fix that in the near future. Okay, so that's the model, and we, as is customary in this case, we applied to present because it's good for this stuff. We found a set of 135 linear approximations over 22 and 23 rounds. And this is very sparse compared to previous attacks, which we use to basically leverage more efficient key guessing. So we can key guess over more rounds, therefore use a stronger distinguisher. Okay, so for 26 rounds we improve the attack complexities a little bit. And then, to the best of my knowledge, we also give the first 27 round attack that actually takes key dependence into account. So this should be a much more realistic measurement of how well you can attack present in this case. Here you can really see the difference it makes that we can pick and choose approximations as we really want to. This this sparsity allows us to guess much more rounds. Okay, that's about it. Thanks.
Any questions? No? Okay, so thank you again.